Hi guys. I think it's just the three of you today. Today we'll be discussing about homework 4. So it's going to be released next week. We'll be discussing about how you are going to implement attention networks. It's going to be a bit nasty in terms of implementation because there's going to be many different parts that you'll have to implement. So the topics for today is we'll be briefly discussing about what attention exactly means. Big Shot spoke a lot about it in class with an example on neural machine translation, but we'll be looking at some other examples with images and another speech-to-text implementation called the Listen, Attend, and Spell paper. And then we'll be looking at a typical structure of the attention networks. Attention networks usually have an encoder and a decoder. So we'll be going over it. We'll be going over the troubles that you might probably face while implementing these networks. And then at the end, we'll be doing a really nice overview over the LAS paper that you'll be implementing in the coming homework. So when we talk about attention in neural networks, it's not really different than how a human focuses on things. For example, if you are looking at some person, if you're looking at some object, you tend to have a Gaussian blur over everything else other than the object that you're focusing on. For example, if you're looking at a screen, if you're reading some letters on a screen, some words on a screen, you tend to overlook some details of how your keyboard looks, even though it is still in your view. So this is how people focus on things while you're trying to read or understand something. Attention mechanisms for neural networks are also loosely based on the same concept. You have some input image that you're trying to understand, but you don't really need to understand the entire image to answer some question about it. For example, let's take visual question answering. You have an image and you ask the neural network to describe what is in the image. So the neural network doesn't have to understand the entire picture, doesn't have to look through the entire picture to answer some so-and-so question about the image. So I will be talking more about it. So this attention mechanism internally, implementation-wise, is just some matrix multiplications. You have a matrix, you multiply it, you have a mask, you do a element-wise multiplication, and you tend to get a really nice map which tells you which areas to focus on. So let's start with the show, attend, and tell paper. So this is an example that Biksha covered in class. It was very brief, but you can see that each of these images is given a sentence, and you're asking to highlight a particular word inside this image. So you see a girl is highlighted by a really nice blob of white mask. So basically, it is an attention map, right? So when we talk about attention, there are two different types of attention. It can be a soft or hard attention. It was covered in class. So basically, you have higher weights for certain areas in an image that tell the neural network to focus on those particular areas. So you basically have a mask, which is all zeros here, but just has higher values where the girl is. The corresponding areas in which relate to a girl are highlighted by the white blob. You can see how each word has a mapping from the word to the area in the image. So how do we do that is basically we generate an attention mask and we also have the images. Once you have an attention mask, you just superimpose it with the image that you have, which gives us a really nice visualization of what exactly the neural network is trying to do there. And people usually use that for error analysis, like which areas are the neural networks going wrong, how do you tune it back, which samples are being which samples are spoiling the network, and other stuff like that. So this is what we'll be implementing in the coming assignment. So we use pyramidal bi-LSTM structure that is going to generate some high-level representations for the decoder to decode. And then we have another layer of bi-LSTMs that decode the high-level representations. We'll be going in much more depth about this just some time. So we saw in class how a weighted combination of the inputs, a weighted combination of the representation of the inputs can help us go from one language to the other, machine translation. So the same concept applies to listen, attend, and spell as well. So you have the utterance, you take, you do some some operations on top of it, and you get a high-level representation of the utterances. Once you have that, it's just about a weighted combination of these, which tell the decoder which areas to focus on. So you see, we have a complete utterance, and you do you pass it through a pyramidal BILSTM network, and then you will have a high-level representation of it. So how do you tell your decoder which areas of the image to focus on? Like, you don't exactly need the complete image to tell the complete image to predict the next word, right? So the whole point is you have an encoder which gives you a high-level representation, and a decoder which gives you a transcript that corresponds to that utterance.
So, quick question.
Yeah.
So, like this piece in between the two networks,
Yeah.
is that to be interpreted as the entire pyramidal flipped and faded?
We'll get to that. There's a lot going on there.
Okay.
So this is just for representation. So the idea is we have an utterance, and you convert it to a high-level representation of some sort, and then you use that high-level representation to generate your predictions, your transcripts. Like, this is the exact same language model that you're implementing in homework 3. So you can amplify these results by using an encoder. Get it right. So you can still predict without using an encoder, but if you use it, your results are going to be way better. Yeah, so typical applications of this is machine translation, which Bhiksha discussed in class, and then speech to text that you will be implementing in the homework, visual question answering. You can read this. It's an optional paper. It's really interesting to read. And then action description, action understanding, all of these, you can probably just take a visual learning course. Yeah, so when we talk about visual question answering, you have an image. So if you're trying to tell, if I asked you a question, how many people are inside this image, what would you do? You would focus on this person, +1 this person, +1 that person, right? You keep moving through the image, trying to understand which areas corresponds to people. So this is the exact same way a neural network would also do it. You basically generate an attention map, and then from that map you can just do an island search to understand which areas contain blobs, and that from that you can just do a counting. You can solve counting problems, and then you can also do a map to understand which areas corresponds to which objects. Like questions like, is there a ball in this image? Is there a shoe in this image? Or is there a person in this image? All of these can also be solved by using attention networks. Yeah, so this is the architecture of the VQA paper. So you have the image. So again, any attention network has two parts, an encoder and a decoder. It might not be very explicit, but yeah, you still have some sort of encoding and decoding going on. So the input image is passed through an encoder. So an encoder here is a bunch of CNN layers. You pass it through it, you get a feature representation of it. You hold it there, and then you have your input question. You pass this input question through a sequence of RNNs or LSTMs, and you get some query out of it. So you have a query, and you have a high-level representation of the image. So you do some operations here, and you try to find which areas of the high-level representation makes more sense for the given input. So with that, you produce a weight distribution of attentions, and then you just superimpose with the image to get a really nice attention map. So this is going to be a basis for any attention network you might want to implement. So these are the papers which showed some really amazing results.
All right, quick question. Going back to the
Yeah.
image. So your weights that you have to your attention,
Mm-hmm.
what is so like how is it turning the question into, it's been trained on that question before? Or?
Yeah, you train it on that basically. So it is probably, I don't know. So all it is doing is learning word mappings from the input question to the images. So what comes together many different times. So if you're asking what color shirt is a referee wearing, you get some high level representation, and you also have the map, which eventually tells you. You keep doing that enough times, you learn mappings from the text to areas in the image, what occur very frequently together. So attention is more about finding mappings from one modality to another modality, or one input to another input. So if you have an utterance and if you have a text, all you're doing is you're finding a mapping from word in the text to some certain areas of the utterance. So you do that enough times with enough number of samples, the network will get very good at predicting which areas of the utterance are important enough to predict the next word. So it's all about that. Eventually you will get a hang of it. Let's move ahead.
Is this attention matrix learnable?
Yes.
Oh,
so you basically learn the weights. You learn the weights of so you learn the con weights, you learn these weights, and when you keep doing the operations of fusing, it's called what do you call it? So you basically just do some matrix multiplications to get the attention maps.
So this is just a way to initialize the attention matrix.
Way to initialize?
Yeah, so from the input question to attention prediction, this is just a way to initialize the attention matrix.
So I think this will be cleared just a few slides down. Yeah. And another application is having multimodal inputs. For example, you have an image and you need to understand it. You have a video and you need to understand it. For example, there's a person speaking in a video and you need to understand his emotion. It is very difficult. I mean, you can still do it by just using images, but it would make more sense to understand what the person is saying and interpret two of these modalities and understand how they work together. And to do this, you have really nice ways to mix these up. You do your typical image understanding, image classification, or other stuff, and then you use the speech modality as a complementary input that you can use to have a much higher confidence score while you're telling what is happening in the scene. So yeah, attention can work in many different ways. It can help you fuse complementary features. Like this example, if you're trying to differentiate between a parking lot and some active traffic scene, you can probably just use speech, audio, and video to do that, instead of just relying on one modality. Yeah, so coming back, typical architecture of an attention network, you have an encoder and you have a decoder. So encoders can be anything. It can be a bunch of CNNs, it can be a bunch of LSTMs, it can be a combination of any of these. So the whole point of an encoder is to produce a high-level representation. And then you use that, you fuse it with the decoder network in some smart ways, and you generate a seed for the next cell that you're next cell in your network. So you keep doing that. The network is not just depending on one input. You can fuse features from different inputs that cover a much wider field of view, something like that. Let's get there in a while. And yeah, in the end, it's just about a simple softmax. You train this, you train a decoder basically, and through the decoder, you train the encoder. You don't really have any labels for the encoder. Encoder is trained jointly with the decoder. Yeah, so these are really cool technologies that are very recently developed. In fact, encoder-decoder networks are like the core technology of Google's translate service, and you will eventually realize the importance of this. So again, let's get to encoders. Encoders are, again, I think I just discussed this, right? Yeah, so let's go briefly how this is happening. So you see, this is a decoder network for the LAS paper that we have. You have the inputs that are coming in from the high-level representations that are generated by the encoder. The decoder takes it, fuses it, pushes it to the next cell, and keeps doing it for every time step. So this happens in a loop. You take a representation, add it to a time step, generate the output, take that, push it into the next time step, and you keep doing that in a loop. So let's get to the main part of the recitation for today. So we'll be discussing about lesson, attendance, spell, paper that you will be implementing from scratch. So this network, as a typical attention network, has two parts, encoder and the decoder. The encoder is named as the listener, and the decoder is called the speller in this paper. So what we are doing here, we are taking utterance. Utterance is just a speech that has been processed. You take it, you push it through a pyramidal bi-LSTM network. So what happens here is, it's just a cool way of doing it. You can swap the entire thing with a CNN, but you just take the utterance, push it, and once you get the output of the first layer, you split it in half and you concatenate the two halves. Just a minute and we'll go through it again. So you do that thrice. The paper asks you to do it thrice. You can do it how many ever times you want to do it based on the GPU space that you have. Once you get to a high level representation, they call it H. Use those features and you generate an attention out of that, and you push those attention context into each time step of your network. So this is important. You are pushing the exact same thing into every time step. So the idea is that the network, the decoder, will learn to map each word to some specific areas of the utterance. So this happens iteratively. Every different word will have a different mapping based on what the utterance is. And once you're done with the encoder, and then you get to the decoder is producing your outputs. The last step would be decoding the inputs, right? Decoding the outputs. So you can use algorithms like the beam search or random search and just get it done instead of using a greedy method. So the idea here is you can use random search in place of beam search because it's very easy to implement. That is the first thing. And the second is you get very similar performance if you have enough number of samples. So we will probably not be discussing much about random search. You will be given a paper. You can read it if you want to. Yeah, so in the previous recitation, Raphael covered how you can pack variable length utterances. So the thing is, this would have been a very trivial problem to solve if you had all of these utterances and transcripts of the same length. But the biggest problem that you'll be having in this assignment is your utterances are of variable lengths and your transcripts are of variable lengths. So you have to pack the utterances in certain ways that you probably have to go through the previous recitation. You pack it and you push it through a network. So basically, this is coming from the idea that you would probably not want to backprop, or you probably not want to use padding while you're forward propagating through the network or while you're computing anything. So PyTorch has a really nice way that you can do it. You can just use some the padded sequences and packed sequences methods to make this someone else's problem. You don't really have to worry about it. Yeah, so what we suggest doing it and what is different in the LAS paper is, in the LAS paper, they have a single output, right? So they only have a single H. So instead of doing that, you can take two outputs out of it, two projections out of the output of your encoder. So the idea is the network learns to generate a key value pair. A key value pair in the sense you use a key to go through the values. So what LAS does is they just use one vector that is coming out, you use that, and you just push it in. So you sort of lose the values that you have, and it doesn't really give you that good of a performance than just using two different projections from the output. These are empirical results that we had from last semester. You can, or it's up to you, you can use it or you could do something else. So what you do is you take two outputs called the attention key and value pair from the output of the pyramidal bi-LSTM network, the encoder. You take both of these, and typically it'll be much more easier for you if you just make them the same length. So the same number of units. The projections are identical. It's just that the weights that are being learned are going to be different. We'll discuss that in more detail in just a few more minutes. Yeah, so again, reiterating it, after each layer of the BiLSTM, the length of the utterance is being halved. So by that I mean that if your utterance is of length L and the frequencies are 40 or 64, whatever it is, you basically cut the utterance in half, so the length becomes L by 2, and your frequency dimension doubles. So it's more like a reshape operation that's going on, a view operation that's going on. You just take this part and you put it on top of it. So that is what the paper suggests you to do. You just concatenate the outputs of the network and stack it on top of it. So you can either do this, or you can just do mean pooling, or you can just do some operation that you think might work better. It's up to you. The paper suggests you to concatenate, but you can do something else. So this is not going to be very easy to implement. It sounds easy. So what the problems that you are typically going to face is, again, the variable length sequences problem. That's going to bite you many times in this assignment. And if you make some silly mistakes, it's going to be very nasty to debug. And so I would suggest just have a very clear idea of what you're doing, put it down on a paper, how the lengths are changing. Just take one example. Make sure the masks are also changing with that. So we'll discuss about masks in a while as well. Yeah, so you have to be very meticulous while you're doing this, because if you get into loops of errors, there's no one who can pull you out of it. You have to start from scratch again. So the way of dealing with variable length sequences is, again, pack-padded sequences and pad-packed sequences that Rafael discussed in a couple of recitations before this. Yeah, so if you can choose to use it, or it's up to you. If you don't want to use it, it's fine. You can still do your own generation of padded sequences if you think you really have the time to spend on it. But people have already done it, so our suggestion is don't get into those troubles. You'll have a lot of other things to face. And coming to the view method, so basically when you have a tensor stored in memory, you store it in a slot, and you only have that slot with you. You don't have memory, any extra memory. You might or might not have it. So what happens is when you try to reshape it, you're taking some variables and you're projecting it into a different dimension. So this might give you some errors in how the memory is stored, because you might have different parts of this variable stored in different sectors. So if you're trying to get it close, view method doesn't really work with it. So I think PyTorch throws an error, but if it doesn't, you probably might have to look at reassigning that variable to a new memory location. It's a simple command. It's called contiguous, dot contiguous, and it takes care of itself. It's just that you understand why that's happening. And then masking is going to be a huge problem, because you're dealing with variable length sequences that keep changing its size from each step, each layer to another. So if you have a length of L here, the sequence is going to be L by 2 in the next step. And with the sequence, your mask is also going to change. So your mask is also going to be in half. It happens with every layer. So if you screw up one single layer, if the mask is off for one single layer, it's going to screw up your entire computation. The problem is with masking is, it's not that you're not going to get results. You are still going to train something, but you will never reach optimal results if you have a bug in your masking. And no one will be able to debug that. You will never understand why your network is failing. So masking is a tough problem. You have to be very careful about that. Yeah, so overall what happens is you have utterances, and you produce 3 different outputs from the encoder. That is our suggestion. It's up to you. Implementation is your thing. But you have 3 outputs. One should be a key, one should be a value, and one should be a mask, telling you which areas of these keys and values are important and which areas should be ignored. Right? So you have a set of variable length utterances. So when you keep dividing it by half, in the end you will end up with some utterances that, and most of them might still be shorter than the length of the longest utterance by 4, right? Yeah, you will understand this while you're implementing it. So you just have to keep that in mind, that your masking is always spot on. So yeah, coming to the decoder. So this is again going to be a bit more trickier than the encoder. Encoder is actually pretty straightforward to implement if you get the masking right. So the decoder is going to be even more troublesome because all this while you're just implementing an LSTM class, which takes care of the looping through the different time steps, right? You never looped through a single time, the different time steps in your network. You always assumed that you just gave in some set of sequences and the network does it for you. So here you are introducing a new attention mechanism that involves you adding some features that are coming from the encoder into different time steps of the network. So the attention context is added at every time step, right? It is added as an input at every first LSTM cell. So for this, you will have to have a much higher level of control as compared to an LSTM class. So there is this class called the LSTM cell class that allows you to deal with specific inputs and outputs to the LSTM cell. So you actually control it. You control what is going into the cell and you control what is coming out of it. So you have the memory state and you have the outputs of the network. It's also called the hidden state, weirdly. So you have two of those coming out of each LSTM cell. You loop through it. You take the outputs. You compute your attention. You add the attention to the adding in the sense you just concatenate with the embedding that is coming out of each LSTM cell and you push it to the next time step. So this happens in a loop. It's going to be a bit complicated to implement. Yeah, so the paper asks you to concatenate the outputs and the attention, but it's up to you to choose it. You can choose to concatenate, or if you want to do some really cool way of combining both of these together, you can do that. But let's just stick to implementing the baseline first. Once you get there, you can try all different sorts of fancy things. Yeah, so key takeaway, you cannot use the LSTM class in this. You have to use the LSTM cell. So it's two different implementations of LSTM. It is a complete LSTM in a pyramidal by LSTM in your encoder and a bunch of LSTM cells looped over in your decoder. Yeah, so a bit of terminology. We will be dealing with different things, queries, context, keys, and values, and energy. So the output from your decoder is a key value pair. And the output that each LSTM cell is giving you is called a query. So you basically use a query to find specific areas in your key to understand, to basically generate an attention map and use that attention map to get your attention context from your values. So let's go through it one by one. So you have a hidden layer. The first LSTM cell can be called as a, like it is a hidden layer, right? You have a LSTM cell which consists of the cell output and the hidden state. You pass some input through it, you get two outputs. Cell output is the cell memory is basically passed on, and the hidden output is called, the hidden layer values are also called as outputs. So you take the output that is coming out of each LSTM cell, and you compute. That output is called a query here. So you take that query, you take the key that is coming out of the decoder, you do an element-wise multiplication of that. So you do an element-wise multiplication to get energy. So once you have, we call it an energy, just terminology. Once you get that, you run a softmax over it. Softmax is basically giving you a really nice probability distribution over different time steps, right? So what's happening is when you just combine both of these, you have a key, you have a query, you combine it, and you're trying to do a softmax. So you're basically telling the network to learn which areas give you the highest activations or the highest outputs for these combinations. So once you get that, you have a really nice probability distribution that tells you which areas to focus on inside the attention, right? Are you getting it? Do you have any doubts here?
So, real quick question. Is the same sequence fed into the decoder as the encoder? Is the same sequence being fed in?
The same transcript, you mean?
Yeah.
Yes. So each utterance has a corresponding transcript, right? So two different things.
Thinking about like a sound file that's variable length,
Mhm.
you're feeding in to the pyramidal LX10, which is your encoder,
Yes.
and you're feeding that also into your decoder.
Oh, so two things here. So you have an utterance and you have transcripts. So the idea is to get from speech to text, end to end. So you just speak something in front of the computer, and the computer needs to generate a text file for it. So you won't be doing complete speech to text. You're already given utterances which are processed. So there's nothing physical here. You have an utterance, you have the corresponding transcripts given to you. All you have to do is, if I give an utterance to the network needs to generate a text output for that, a complete speech to text engine, right? Yeah. So the keys basically are outputs of the encoder network, which is a high-level representation of your utterances, and the query is a representation of your transcript or the word embedding that you give it, right? So you're basically trying to find a mapping from the word embedding to areas inside these utterances, or the representation of these utterances. Yeah. So what you do is you take the key that is generated from the utterances, you take the query that is generated from the word embeddings, and you fuse it. You fuse it, and then fusing here is basically just element-wise multiplication. After you fuse it, you run a softmax over it to get a probability distribution of which areas of the utterances or the combination of utterances and the text embedding or the word embedding is giving you highest results. Once you get that, it is sort of like having a map, isn't it? So you get to understand which areas give you high outputs and which areas don't really give you high outputs. You do that enough number of times and you get a really nice attention map by just doing a softmax over the energy. You take the attention map, and then you have another set that is generated from the network, another projection, which is called, we call them the values, right? So this is why you use values. You take the attention map, you apply it on top of the values. Applying it is basically just another element-wise multiplication. So you have an image, you have some 2D or one-dimensional representation. You have a map that tells you which areas to focus on and which areas to let go. Once you superimpose both of it, you'll only be left with areas that are important inside the image, right? It's like focusing on specific things instead of just wasting time around seeing pixels that you don't really need. So that is how you get your context. You just use the attention map over your values, use your context, and you take this context, you just concatenate with the inputs to the next cell, and you keep repeating it at every loop. So this, honestly, attention is probably the simplest thing to implement here. The biggest problem would be how are you dealing with masks again? Yeah. So this is what they asked us to do. You can just concatenate, or you can mean pool, do whatever you want. Let's just stick to the baseline first, and then you can probably look into other cool, fancy stuff. Yeah.
And just to be super clear, when you talk about problems with masking, it's mostly like problems with variable length.
Yes.
How
Yes.
do you
Yes.
you then have to cut that out as you're training it.
Yes, exactly. So I keep mentioning the problems of masking because around more than 50% of people got stuck in this last semester. So you really need to know that masking is going to be a problem if you're sloppy about it. And you're not going to get out of it. You'll have to start from scratch. These are nasty problems that you might get into. So you have to really be careful while you're implementing it. It's very easy to get lost. Yeah, so let's look at the entire picture now. Encoder, decoder, you cannot train the encoder without the decoder. So encoder is basically generating values for the decoder. Like there are some really cool ways people have been doing it, like generative latent optimization, I guess. But I still don't get that shape, honestly. So you typically need the decoder to train your encoder, because encoder is basically teaching itself the most optimal values to generate so that the decoder can perform well, right? So decoder itself is a standalone network. It can work very well even without the encoder. Encoder helps it boost the results in many magnitudes. Yeah, so another problem with PyTorch is you don't really have a graph to show you how the tensors are flowing inside. So it is going to be really difficult to debug problems that come in the connections between both of these. So you might think that the network is learning, but at times you would realize that there is no backpropagation going out for the encoder network. So these are also some really difficult problems. You have to be careful, and if your network is not really performing as good as it should, it probably could be a reason that the connection is broken. So there is no flow of tensors from the listener to the speller. Yeah, so another suggestion here is try to keep the code as simple as possible when you're dealing with this, because there are so many different parts. It's very easy to get lost. And if you have some really fancy code structure, I don't think any TA could also help you, because things keep flowing around so badly. It's very difficult to keep track of it. So contain code, keep it really nice. Don't use functions where you don't really need them, because it's just complicating things, right? Keep it simple so that it helps you with debugging. Yeah, again, masking. Any questions? Okay. So masking, again, could be a huge problem, as I've been reiterating it. Why? Because you'll be doing a lot of squeezing, a lot of concatenating, a lot of changing dimensions, unpacking, packing. So even if you're wrong at one single step, the entire process goes wrong, right? So your packing is off, your unpacking is off, you're training right from the start to the end, till the time you compute your softmax, till the time you compute your loss, it's going to be flawed. So you have to keep this in mind. Yeah, so we've discussed about how variable length is important. And speaking about it, the whole point is when you're backpropagating through values, you need to ensure that you're not backpropagating through padding, right? Padding should not, the effect of padding on backpropagation should be 0. Like, you should not be wasting time on it. So the simplest way you can do it is you just take your outputs till your loss, and you just take them. You also have a mask which is coming with you till the end. Just do element-wise multiplication, and then you backpropagate through that. Because if you're going through zeros, it doesn't really make any difference. Loss is basically computed on a scalar, right? So if you just zero out the outputs and you sum it up, there is no influence of the 0 elements on the sum. So it's not going to affect your computation. While implementing, you will understand it. Okay, so another thing is we spoke about how to train it, which is really cool. But another problem that you will be encountering in language models is the model getting stuck in predicting loops. Like, you keep predicting errors and you don't ever recover from them. You just keep predicting the wrong things. So you can use a trick called teacher forcing. Yeah, let's start with teacher forcing. So teacher forcing basically helps the network not predict errors. So what you do is at times, so generally when you're training a language model, you only give it the ground truth, and you correct the output that you're getting based on the ground truth, right? So instead of doing that always, instead of just using the ground truth to train your language model, at times you just take the output of the network and you push it into the next state. Getting it? So instead of just using ground truths, you take the output of the LSTM at that time step and you push it in as the input for your next time step. So in this, if you do this, what happens is, if your network is generating some wrong words, you also teach the network to recover from those errors, right? Even if you predict one wrong character or one wrong word, you can get back and you can get to the original sequence that you have. So this happens, you should not be doing it forever, because that would just train the network to produce rubbish. So this would be based on some probability that you decide. So if it's a probability of 0.5, 50% of the time you'll be using your ground truth to train it. 50% of the time you'll be just taking the outputs of your network to push it in. So this helps play around with dealing with errors. You should probably not be having 50%. What was any idea what the ideal value was for teacher forcing? 0.2 or something like that, isn't it? 0.1. Yeah, 0.1. It should be very less, just to deal with errors and not to get stuck in loops, obviously. Yeah, so again, so we spoke about how the decoder works. It's a language model. All of you have been implementing it in homework 3. So if you look at it, this is a really tough problem to solve, right? First, the network should learn to decode, then the network should learn how to encode. It happens jointly. So instead of that, what you can just do is you just train your language model first. Train it as well as you can. Save those weights. And once your language model is trained, now you can add your encoder, use it to amplify your results. So this sounds really cool in practice. This sounds easy to implement as well, but it would have been easy. But we are adding another part for the network, so it might not be that trivial. You have to add context. You have to append that context to every layer. So this might be a bit complicated based on how good you are at code. And you have to load the weights cell by cell or layer by layer. It's going to be some effort, but it's definitely going to save you a lot of time. So it might be a really nice concept. You would want to learn using pre-trained weights. It's going to help you a lot in other assignments as well. If you're going to do a project tomorrow, so it might be very helpful. And lastly, you have a really nice trained network, and you still are not getting to the top of the leaderboard. Why could that be? It's probably because you're just using a greedy algorithm, right? You're just using a greedy search. So there are some really nice ways in which you can get done with this. Probably use beam search, or beam search is a bit complicated to implement. But if you've done the bonus for homework 3 part 1, you could probably just use that code. Or you can just use random search. Random search empirically has given really good results for us last semester. And it also takes much lesser time to implement as compared to beam search. Okay, so we spoke about attention keys. Yeah.
So, are we not able to use the decoder we used in this homework?
I'm sorry?
Are we not able to use the beam search?
You can use it. That is what I've been suggesting. You can use beam search if you have the code.
Sorry, you're saying if we implemented the code, we can use it. Right now, we haven't implemented it. We're using a package that they've given us
For beam search?
for beam search for this.
Okay, so you can. So are we allowing them to use packages for beam search?
Packages from
No.
So Ryan gave us a package for beam search.
Okay.
You did?
Yeah, he said like download this code because it's bonus to implement beam search.
CDC decoder.
You sure?
I actually has that. Yeah.
There is the package for CTC.
CTC has a package.
So is there another
There's also a
package?
package for beam search. Yeah.
Oh, you
Okay.
go.
So you just sold out Ryan.
Sorry. And I'm
Okay.
doing it as well.
Yeah. Professor's going to be seeing this. Yeah, so you can use beam search if you implement it, but I don't think we'll be allowing you to use packages. Okay, so we've been talking about projecting the outputs of the encoder into a key and a value pairs, right? So by projection, we just mean that you can take the output, you take the high-level representation, and you use linear layers to push it out in 2 different streams. So we would suggest that you use a linear layer of size 256 because it's given us really good results, and going any higher than that, I don't think it's necessary. It would just be eating up space, and if you want to try it, you can try it, but we just suggest you use 256. It has given us really good results. Yeah, so this initially might be a bit confusing. You might be thinking, why do I have to take 2 parallel projections out from the same output? It makes no sense to me. But think of it this way, right? You need the exact same dimensional outputs. You use one to get to compute the attention, and use the attention to get the context out of it. So it is like a really nice triangle. You use this, compute the attention map, use the map to get the context out of the values that you have from the direct output of the network. So this is really nice. You will probably understand it more when you read the paper. But yeah, just stick to the size that we've given you. It should work. And again, reiterating, the output of the encoder could be anything. It can be a CNN, it can be some pyramidal bi-LSTM network that they've given. If you want to be fancy, you can just mix up the CNNs and LSTMs. It's up to you. It's totally up to you. Just try to use the variant that we suggested you. If you want to use the baseline variant, it's up to you. But this gives you better results. Yeah, so any doubts on how we are getting the weights of one projection and use those to compute the output, the context, and you use the context to get through the decoder? Any slight doubt there? Yeah? No? No? Okay. That's fine. So implementation of attention. This is how the shapes keep changing. So just so that you don't get confused eventually, you can have the L and B as a same size. We just started off saying that you can have different lengths of the key and value pair, which in theory you can. But if you want to keep it simple, you can just have the exact same projection on two different parallel outputs. It's way easier to implement if you think about it. So repeating it, first, the decoder produces a query from a word. You have a word embedding that you're pushing it into the LSTM cell. You have some output. You hold that output, call it a query. So the network tells you that you have to do it for the first layer. You can use it for the second layer. You can use it for multiple combinations, first layer and second layer, only first layer. It's totally up to you. You can add attention in any layer that you want to. So first, in any case, if you're doing it, first you get a query out of an LSTM cell. The query, let's suppose you have the shape is n cross A, A being the length of it, n being the frequency or the number of, okay, this is the batch size, I think so. Yeah, and then you get the query. You use that query to compute attention map from the key that you have as the output of your encoder. So basically you just use element-wise multiplication for that. You take that, you multiply each element with the corresponding element. You can only do that if you have similar sizes, right? So once you have that, you have an output of this. We'll call that energy. So the first step gives you a query. The second step gives you the energy. It's just terminology. You take energy, and then with that energy, you compute an attention map. So how do you do it? You just use a softmax over all of those values. You get a really nice probability distribution of which time steps that you have to focus on the utterance, because utterance is basically on time, right? The length is time. And then you get the attention map. And with that attention map, you just do another element-wise multiplication with the values. Is that sinking in? You need to be very good with these concepts before you implement it. So you get the attention, just concatenate, and you just repeat everything we've spoken about before this. So yeah, it's going to be a short recitation. Word of advice: this is going to be really heavy to implement. It's going to take up a lot of your time. If you're planning on starting it just 1 week before the deadline, you're not going to make it. Most definitely not going to make it, because you also have to factor in all the bugs you'll have to debug. Yeah, and so there is, if you're planning on waiting till the end so that we give you a baseline, it's not going to work, because we already gave you a baseline. The LAS paper is the baseline, so you just have to implement it. That's all you have to do for homework, to be honest. Just implement the paper, get to the top of the leaderboard maybe. And the cutoffs are going to be high, because it's going to be higher than last time. High in the sense lower than last time, because we are giving you a lot more information than we had. We just had a paper and a few posts on Piazza last semester, but you have an entire recitation that went through how you are going to implement this. We had an entire recitation on how you're going to deal with variable length sequences. So the cutoffs are going to be tougher, and I believe the competition is also going to be fierce as compared to last semester. And yeah, again, just keep everything simple. Just don't have 10 different files for different functions or different classes. Try to keep it structured. Minimize the amount of code that you're writing. Just make sure that you don't use different functions if you're just going to call it once. Like the rule of thumb is if you're going to use more than 5 lines, more than thrice inside the code, you just make a function for it, right? If you have one single line and you're going to use it twice or thrice in your implementation, you don't have to make a function for it. It's just complicating your implementation. So make sure you follow some good coding practices so that TS can help you what exactly is going on in your code. If the implementation is wrong, you'll just be wasting time at the office hours. You'll be wasting your time debugging. Just try to have a really nice structured code. So that's about it. That's all for today. So do you have any questions?
So this is the last homework, right?
Yes, this is last homework. Yeah, this is the last homework. And we are not going to be having different parts for this homework. It's just going to be one part. And you'll be getting more than a month to implement this. So if you think about, if you want to know what the load is going to be for this homework, just take this into account that homework 3 was just for 2 weeks, and this is going to be more than a month for a single part. Yeah.
Is it?
Yeah, I mean almost a month.
Did you get that?
What?
Oh, my God, yes.
Yeah, that was,
That's actually true.
yeah.
Okay.
Okay. Thank you then. Thanks for coming.